It's not a book for beginners. He doesn't prove very much. On occasion he does something, but as a reference, it's an excellent book. A couple of things he explains, and other things he just refers to the literature. So it's a good book. And he does really everything, a lot of things in Riemannian geometry, not just Einstein manifolds. He does scalar manifolds and holonomic groups and all kinds of stuff.
I'm looking at a book of doutorado2012.
Okay, that's, yes. Yes. Mm-hmm. So that's a standard reference for holonomic groups nowadays. It's just holonomic groups, I think, right? The title?
Two books. The first is Compatible Manifold and Special Holonomy, and the second is Calibrate Geometry.
The second one, I don't know. The first book I know. Okay. Hi. I can explain the principle again if you want to, in this holonomic principle that you mentioned. I could discuss it a little bit right now if you want to. Okay. So his question was the following. So first, let me remind you that we had the holonomic group, just a set of all-path stations. Gamma was a closed path beginning and ending at P. Inside here we had the identity component, which I could also describe as parallel translation, or gamma was null homotopic. And this was compact. And if pi1 is equal to 0, then all P is connected. So these are the three main properties about holonomic groups that we mentioned. So what he was asking, what was a holonomic principle? Maybe do this in a little bit more detail. So here our point is fixed, right? And then I have the tangent space at the point M. And now on this tangent space, I can find a tensor. Say, let's call it L maybe. So, for example, there's several ways to describe it, right? So, depending on what the type of the tensor is. So, part of the tangent spaces in their dual, right? So, if I do this up to Q times, let's see, K times and L times, this is a tensor of type K, L. But you've seen this before, right? Tensor of this kind of type. When you have such a tensor, you can also define the coherent derivative of the tensor. Do you know how to do that?
The typical compensation.
Pardon?
I define it by evaluating.
So let's. It's again a tensor of the same type. Right. So this is going to be K plus 1L. My new argument is the element X in which I differentiate. Right? And then say I have here Y1 up to YK. What's the best way to define this? Well, it's maybe an equivalent way to define it, which is slightly more convenient now. It's a linear map from tangent space to tangent space. Well, this is K times, this is L times. Okay. So then this here would have to have L components, and I differentiate each one separately. So take L, apply to nabla X, Y1, Y2 up to YK, and then alternate. Right? So differentiate each component separately and then add them together. Right? And then that's not quite a tensor. If I do it in this way, what do we have to do next? I have to subtract something from that. what?
Connection on X.
Okay, so let me do it for maybe a tensor of type 1, 1, so it's easier to write down, right? Linear map. How do you differentiate the linear map? So nabla XL applied to Y is nabla X applied to LY minus plus minus L applied to nabla XY. I think that's what it is, right? Of course, if you have several arguments now, you do the corresponding thing once in each component, right? Do this in each component, do this in each component, add them up together. Okay. So this becomes then a tensor of, so this here is type 1, 1, and this here is in type 2, 1. So the extra argument is just the direction in which I differentiate. And now you have to convince yourself of the tensor again, right? So linear over functions. So that's how I would define the co-derivative of a tensor. And now the whole normal principle is that if L is a tensor on TPM, invariant under Hall P. So what does that mean? So if, say, H is an element of the holonomy group, right, that's a linear map from the tangent space to the tangent space. Invariant means that if I plug that in, this becomes H applied to L. Well, so now I have to say what the type is. Let's make it into, say, type K plus L, 0. Right? By plugging it into the argument here, I can always make it function valid if I want to. Right? And then it would simply be that this is L. So the natural thing that I would write down for being invariant. Right? So it's a tensor that's invariant. Once I have that, I define a tensor on M. Let's call it L bar. I look at my fixed base point P and take at any point Q. Take a path from P to Q. And then L bar at the point Q is defined as, so L at the point P, pair translation inverse, and pair translation back. So from Q I go to P, I take the tensor, then I go back to Q. Okay. So that's now a tensor at the point on TPM, on TQM. Okay. Now you have to observe it's well defined. Because if I have two paths, then the pair translation along gamma, gamma 1 composed with gamma 2 inverse is by definition an element of the holonomy group. And that means that if I do it with respect to 1, I guess it doesn't matter. I get the same value at the point Q. So now I have to at least a well-defined tensor at all the points. And now,
do you have to conjugate there?
Pardon?
Do you have to conjugate there?
Where?
In LQ, because it's already a K plus L 0 tensor.
You talking about this equation?
Yes. In the output, do you have to put the parallel transport on the output?
Okay, you're right. If it's a K plus L0 tensor, I don't need this. Okay. Exactly. Yeah, it depends on whether it has vector values or function values. Right? If it's vector values, I have to apply it again. If it's the function value, then I don't. You're right. Okay. So now I have a well-defined tensor on the manifold, and now I prove two things. First, that L bar is smooth. And the second property is that the co-derivative of L bar is equal to 0. How would one prove it's smooth? Any suggestions how to prove it's smooth?
A suggestion and a question.
Okay.
The parallel transport is smooth depending on the path.
Mm-hmm.
So if I vary the path smoothly, I will have something smooth. So that proves the L bar will be smooth.
So what's a canonical family of paths?
Which is what?
What's a canonical family of paths which depends smoothly on the parameter?
I take a piecewise path. I take a gamma, and then I continue by radial geodesics.
Okay, yeah. So that's the I want to prove it's smooth at say gamma naught, gamma 0, right? I have my point P here. That means I have to prove it's smooth in the neighborhood of the point Q naught. I now just compose with radial paths like this. So gamma up to point Q and then radial here. It's independent of the path, that's implicit over there, right? So this defines the tensor at every point in the neighborhood. Now the radial geodesic certainly depends smoothly on the beginning point in the direction. And now it becomes smooth in the neighborhood. Okay. So I choose these kind of paths separately for each neighborhood if I want to.
But if I have some other way to determine the path smoothly, I will also prove that this tensor L bar is smooth.
Correct?
So the autonomy is essential for making this global and for the next property.
And what?
And for the next property.
The co-derivative 0? Or what?
That is parallel.
Okay, so how do you prove it's parallel?
No, I was saying like being smooth is not the main part.
No, of course. I mean, this is just, if it's not smooth, it wouldn't be interesting, right? That's a technical point. The tensor defined this way is smooth, right? Just something easy to check, exercise. This is the important part. This is where it comes in, that the way we defined it is by using a tensor that's invariant under the holonomy at the point P and then moving around with pair translation. So why does this imply that this is equal to 0? There's another way to define the co-derivative.
Because you take values, vectors, to evaluate on at Q, and you can look them as parallel vector fields.
Even better than that, maybe it's the same thing you mean, say, write X as gamma prime of 0, or gamma is some path, right? And then write this as via pair translation along gamma of t. I pull my tensor back into the tangent space at gamma 0. And then I differentiate with respect to t at t equal to 0. It's a very geometric way of saying what the derivative is. Take any curve in the direction of x. Doesn't really matter what the curve is, independent of the curve. At each point there, I just pull back with a pair translation to the original point. Now I get a curve in a linear vector space, then it's clear what it means to differentiate. And that's another way of interpreting the co-derivative. Of course, now it's clear, right? Because this here is equal to L bar, no matter which path I choose here. So this becomes a constant path in tangent space, and therefore the co-derivative is 0. So I get something that's parallel. So that's the holonomic principle, right? Carried out in more detail. By the way, to prove something is parallel, there's another equivalent way of viewing this, which is sometimes useful, namely if x1 up to xk plus L are parallel, and applying that to the tensor, is parallel or constant, right? So if it's function values, that's a constant. If it's a vector value, it would be a parallel vector field again. So it takes parallel things to parallel things, right? That's an equivalent way of formulating this. You can check this out. In fact, notice that this is where you need an equation like this here, right? If this tensor is 0, then parallel means L of a parallel vector field. This one would be 0, would be parallel again. Okay, so if this is 0, this being 0 implies this being 0, and then conversely also. So that's another useful way of thinking of parallel objects, that they take parallel vector fields to parallel vector fields. Does that answer your question? Okay. Then we discussed one other application of whole number groups last time. I'm going to come back to these whole number groups later on, once we know a little bit more about symmetric spaces. Then I can describe all whole number groups of Riemannian manifolds. There's a very nice explicit description in terms of symmetric spaces. So this was a de Rham theorem. So M was complete and simply connected. And I look at the whole number group at some fixed point, which of course is the same thing now as identity components, a connected group. And I split the tangent space into subspaces. Such that on V0 it acts trivially. So that's a linear subspace clearly. And then it acts irreducibly. So whole P of VI is contained in VI. And it acts irreducibly on VI. So no invariant subspaces. So this was the assumption. Conclusion was that M then splits as a product corresponding to the splitting at a point where M0 is isomorphic to Rn, so with the usual metric. And Mi are irreducible, and the tangent space of the MIs is isomorphic to Vi, where I have to regard in a natural way the tangent space of the MIs as a subspace of the tangent spaces M, as I usually do for an inner product. And then the two additional properties were that the whole number group splits. And the isomorphic group splits. At least the identity component splits. And in fact, the splitting here was unique up to order. That was also important. Okay, so this was the de Rham decomposition theorem. Now let's apply that to symmetric spaces. So one thing we proved last time was that if G mod K is a symmetric space, G is the isomorphic group, the full isomorphic group, and K is the isotop group at subpoint P, then this implies that whole P is contained in K, where we observe that certainly whole P acts on TPM and K via what we call the isotropic representation, which just takes an element K into the derivative of the point P. So since it fixes the point P, that's well defined. So then whole P is contained in K. So that we proved last time. This motivates the following definition. For a symmetric space, So here in this Durham decomposition theorem works very nicely when M is simply connected. If it's not simply connected, then things get complicated. In fact, this is always written down in the simply connected case. Of course, if I have a manifold that's not simply connected, I can look in the universal cover and then can apply Durham there. Right? But when I look at the subcover, things may not be a product anymore. Let me just say, for example, let's say I take S2 cross S2 and with a product metric that's simply connected. I can now look at, say, a new manifold, which is S2 cross S2 divided by identification, which takes X, Y into Y comma X. Except I can't do that because I have to be fixed point. Let's do it as minus Y comma X. So notice now this is a order 4 group. I guess it's C4. There are no fixed points because X minus Y, YX can't be. So the quotient is a manifold. Right? But I now switch the two factors. And therefore, this is irreducible. So in other words, it's not a product of two factors like S2 cross S2 is. Right? So when I take a subcover, things that are product upstairs will not be product downstairs anymore. So this is usually formulated only in the simply connected case. So I want to make a definition for a symmetric space. Then M. M is called irreducible if the group K naught acts irreducibly on the tangent space, where K was an isotropic group at that point. So here, I take the identity component of the isotropy, and I assume that acts irreducibly in the tangent space. So maybe to not confuse these two things, it's better to say that MI is indecomposable to differentiate from irreducible for a symmetric space because it's not quite the same. In the literature, it's usually called irreducible. For our purpose, I'm going to call it indecomposable if it's not a product of other manifolds in this sense, a Riemannian product of other manifolds. Right? And the splitting here, the metric is also a product metric. So let's motivate this definition. First, notice that if the symmetric space is simply connected, and G mod K is indecomposable, then G mod K is irreducible. So the other way around? Other way around. If it's irreducible, then it's decomposable. So let me switch that. You see the other way around does not hold in this triviality. G naught is irreducible, then G mod K is indecomposable. As a Riemannian manifold. Right, so let's call this M again. Proof is very easy. Well, if M is decomposable, then M is a product. And the isomorphism group then splits. The identical component of the isomorphism group splits, and hence K also splits. Well, that's not a lucky notation now. So to see this, all I have to observe is, so notice that K is connected. Since pi 1 of G mod K is equal to 0, this implies K is connected. K is connected, lies inside the isomorphism group. Therefore, it also must also split into factors like this. So I don't know if you remember this fact over here. This was in fact very easy. Because we always have a covering from G mod K0 onto G mod K, if K is not connected. Covering as many components I have for the group K. Right? So since it's simply connected, that's part of the assumption here, K is connected, and therefore it also splits. And Ki preserves the tangent space of the MIs. By definition. Okay. So it acts reducibly on the tangent space. So irreducible implies indecomposable, but indecomposable doesn't necessarily imply irreducible because of this example. Right. So the converse is not true. So G mod K decomposable does not imply G mod K reducible. So so the example would be like S2 cos S2 again divided by xy goes to minus yx. This is not a product. Is that the example I want? It is an example, but that's not the one I want to give. This is a little bit more difficult to show this example, but here's an easy one, in fact the more important one, because it's even simply connected, so even the simply connected cases is false. You might think, well, in that case it would be the same, but that's not quite true because of the following example. So take Rn with a flat metric, then I of m is the orthogonal group, direct product with translations. That's the full isomorphism group of Euclidean space. And what is K? Fixed point isotropy of the origin is just the orthogonal group. And if K acts irreducibly on the tangent space at the origin of Rn, clearly, right? So this means that Rn is irreducible as a symmetric space. But of course, not indecomposable. It's a product, right? But not indecomposable. At least n if bigger than 1, right? It's a product of lower dimensional Euclidean spaces. So that means it's kind of, if you want a strange definition, you might think that's a strange definition, but we're going to see it's actually very natural if I want to prove things. And this example is essentially the only counterexample. So we're going to prove that if it's a symmetric space, you look at universal cover, and if Rn splits off, you forget about it. And then for the rest, it's irreducible if and only if it's indecomposable. So in the end, it's going to be the same except for this kind of special example. But right now, this is important. Why do I take the identity component? So what's a good example for that? So it's again the example S2 causes 2 in the following sense. So if I take S2 cos S2, say with the product of the round symmetrics, what's the isomorphic group of M? Well, certainly the isomorphism of each factor. Right? So it's O3 cos O3. Okay, now I can do one more thing. I can switch the two factors. That's not isometry. So union, I don't know what I call it, reflection, if you want to, times O3, O3. So R of xy is yx. That's next isometry. That isometry fixes some base point. So let's take as our base point, say, x, x for some x naught on the 2 sphere, like North Pole, right? And then what does the isotropic group at the point P look like, which is what we call K? Well, it's the group inside O3 that fixes a point, say the North Pole. This would be an O2. So I get an O2 cross O2. But the reflection also fixes this union R times O2, O2. And now you see that the K acts irreducibly on the tangent space of S2 cos S2 at this point. Because it's, switching the factors is also included in there, so the only naturally invariant subspace are each factor. But since the switch lies in there, there's no irreducible subspace. So K acts irreducible in TPN, but of course K naught does not. In fact, right, by de Rhams' theorem, which I just erased, the identity component of isometry just splits up. So if I look at the identity of the isotropy, it can never switch factors. Must always preserve factors. Okay. Of course, this space, you don't want to call S2 cos S2 irreducible as a symmetry space. Right? That's not a good idea. But in this sense, it's irreducible. So since I take, it's reducible. Right? S2 cos S2 in this sense is a reducible symmetric space. Okay. So these are some examples which motivate the definition. Okay, so application of the de Rham decomposition to symmetric spaces. First one. Maybe two. If G mod K is symmetric and simply connected, then it's a product. In fact, here I don't have to separate this, where Mi irreducible symmetric spaces. in the sense over there. So every simply connected symmetric space is a part of irreducible ones. Particularly when I classify later on, it's sufficient to classify irreducible symmetric spaces. And that proof follows easily as follows. So recall that that Hall P is contained in K. Okay. In fact, Hall P is the same thing as Hall P0. So take the tangent space at the base point P and write this as sum of irreducibles. And of course, I could again be a subspace on which it acts trivially, so maybe we want to include this after all. So K TPM is W0 plus WK, and the group WL. K acts irreducibly on Wi, I bigger than 1, and trivially on W0. Hall P is contained in K. That means Hall P also preserves the decomposition, but of course the decomposition may not be irreducible with respect to Hall P. That means each subspace could split into again, a direct sum of irreducible subspace under the group Hall P. So let me just say it in words. So this splits again. This splits further. Into Hall P irreducible subspaces. And corresponding splitting of M according to the Dram decomposition theorem. Now I have more factors than the Wi's, but I collect factors. Right? So if W splits into a certain number of factors, I just collect those into one MI. And so hence M is equal to M0 cross ML, where the tangent space of the MIs are equal to the WIs. So one of these M's may not be indecomposable as a manifold, because it might be a product under this possibly smaller group, but as collect them, I put them together. Right? And now, of course, by definition, the group K acts irreducibly on the MIs, and hence MIs are irreducible symmetric spaces, except for I have to convince myself that's a symmetric space. So right now I have it as a product of Riemannian manifolds. Given a point P, I can then split it into P0, P1 up to PL. I have a symmetry at the point P because I assume that M is symmetric. This is my symmetry. And now I claim that if I look at the derivative of the symmetry at the point P, that is my identity. I now look at this as acting on W0 plus WL. This, of course, preserves the WIs. And hence, I can write SP as SP0, SP1 up to SPL, where each one is the component of the isometry which preserves the ice factor. And of course, then derivative of SPI is again minus identity. And this implies that MI is symmetric. Okay, that's it. So each factor is symmetric, and by construction, because Kx irreducible W is an irreducible symmetric space. We come back to this question whether these groups are the same or not here. They may not be the same. And the example, again, whether they're not the same is Rn. And that's essentially the only one. So if M is flat Rn, K0 is then the special orthogonal group. That's the isotopy of the point. But of course, all 0 is just trivial because pair translation doesn't depend on the path, right? So this group is trivial, and this group is a full orthogonal group, so as far apart as you want to. Right? But that's essentially the only example. So we're going to see later on that if in the universal cover I don't have anything that splits off as a factor, then these two groups are actually the same. I'll come back to that. Okay, so that's the application of the de Rham decomposition theorem to symmetric spaces. Maybe one more application that's important.
The last assertion, can we prove it right now, or we need more?
That's the symmetric space?
No.
Or what?
If the universal cover, you don't have products, then the autonomy is...
Oh, no, that's not clear at all. You can't prove that yet. No, that's not clear at all yet. I'm just saying it kind of as a motivation that this isn't so bad the way we define irreducible symmetric space. Right? That this Rn we can take care of later on, but it's not clear at the point right now. One more fact. It's useful and maybe motivates, again, this definition also. If G mod K is an irreducible symmetric space, then first the metric is unique. Up to a multiple. Of course, I can take the metric, multiply a constant, I get another metric, but it's unique up to that trivial cannot change, and the Ricci curvature is constant. For some constant lambda. These are called Einstein manifolds. So these irreducible symmetric spaces are an important example of Einstein manifolds, very natural examples. Have you seen a proof of such things? Let's think of the first one. Why is the metric unique? So what do we know? We know that K naught acts irreducibly on the tangent space at my base point M. Right? Metric on TPN determines the metric everywhere. Right? Of course, left translation are isometries. Right? So if I know it at one point, I know it everywhere, because the group acts transitively. When you G of isometry, it acts transitively. So I can concentrate at just what happens at the base point P. And of course, K acts by isometries with respect to the inner product by definition. Right? And K acts reduced from the tangent space. So there's a certain lemma that one uses now to finish the proof. Schur's lemma. Do you know something called Schur's lemma? There's several versions of it, but the version we need now is the following formulated. It's a very simple proof. So V is a vector space. V1 and V2 are symmetrical linear forms. One of them non-degenerate, say V2. And both invariant under rule K that acts irreducibly. On the vector space V. Conclusion then is that there exists a constant lambda such that B1 is a multiple of B2. Have you seen that before? So we can not say how to prove that, but I claim this finishes both things, right? So I have my inner product in tandem space. It's invariant under K naught. Irreducible symmetric means K naught acts irreducibly. So if I have two inner product, one's a multiple of the other. Okay. For the second part here, well, the Ricci tensor is a symmetrical linear form. Curvature preserves the curvature. Isomers preserve the curvature. So it's invariant under the action of K naught also. That's invariant under the action of K naught. This one is non-degenerate. This one may not be. But it doesn't matter. The one that's possibly non-degenerate is a multiple of the non-degenerate one. Okay. So that's the most general version of this kind of Schur's lemma. One often sees it only formulated for non-degenerate ones, because they both are, but you don't need that. So what's the proof? How does one prove that? For those who've seen it before. There's a trick that one often does if you have two inner products or two symmetric forms. You can write one in terms of the other. So I claim there exists a linear map L from V to V such that B1 of x comma y is equal to B2 of Lx comma y for all x, y in V. Right, so how do I see this? I want to define Lx. Right, so I have x given, I want to define Lx. I can define that by taking the inner product with any y, because B2 is non-degenerate. That will determine this argument here. So I can declare the inner product simply to be 1 of x, y. Here I don't need non-degenerate B1, only non-degenerate B2 to do that. Right. What property does L have? I claim L commutes with the action of K, just because both B1 and B2 are invariant. So let's see, B1 of Kx, Ky is equal to B2 of Lkx, Lky by definition. But now K also preserves B2, so that's the same thing as B2 of K inverse L K x comma y. And of course, this here is the same thing as B1 of x comma y, because B1 is invariant. So here I use invariance of B1. In this step here, I use invariance of B2. Of course, this is now true for all y here. I'm not quite there yet. Why is this equal to L? I think I did it maybe the wrong way around. So I want to now conclude that K inverse LK is equal to L. So this here is now, furthermore, B2 of LXY. Okay, so now this is equal to this. That's true for all Y. B2 is not degenerate. Therefore, L must be K inverse LK, or LK is equal to KL. So it commutes with the action of K. And now I can use one version of Schur's lemma, but in fact, you can see this immediately why this is impossible. So I need one more property of L to finish this off. Pardon?
L may be representation.
K is representation on the vector space V. K commutes with L. I think I also need that L is symmetric. I want to claim that I need one more property, that L is a symmetric endomorphism. Although I think in this generality it might not be true. So the next observation is I claim L is symmetric with respect to B2. One thing I haven't used that these are symmetric. I haven't used that these are symmetric bilinear forms. Otherwise, it's not true either. So why is L symmetric? So I claim that B2 LXY should be B2 XLY. That's what symmetric means with respect to the inner product. Well, what is B2L? This is B1 XY by definition. And this here, by symmetry of B2, is B2 LYX. By definition of B1, that's B1 of YX. And these are equal to by symmetry of B1. Okay, symmetry of both of them together implies that this endomorphism is symmetric endomorphism. Okay. And now I can say use Schur's lemma, or if I want to, you can say it in words right away. Why is this a contradiction? If I have a symmetric endomorphism, what can I do? I can diagonalize it, right? Or write as some of the eigenspaces. If I have something that commutes with it, what does it do?
Can we diagonalize the same basis?
Yes. Or if you want to, so.
Well, it takes thing vectors to equal.
If, say, V naught is an eigenspace of L, then K V naught is contained in V naught because it commutes with it. It commutes with it, preserves eigenspaces. That, of course, if it's irreducible, this implies that either V naught is trivial or V naught is equal to V. So take a non-zero eigenspace, but there must be something that's non-zero because B1 should be non-zero. Maybe that should be part of the assumption, right? That these are non-zero. So there must be non-zero eigenspace, and that's preserved. Therefore, that space must be everything. Okay. Of course, that means then on this there exists a lambda now, such that L is lambda identity. Where lambda is an eigenspace which is not equal to 0. And this means that B1 is lambda B2. Okay. If B1 and B2 are not symmetric, this may not be true. That's a good question. L is an isomorphism.
Yeah. Maybe it's kind of a rotation.
It's an isomorphism, commutes with the representation, but it's a real representation. So I think what you're thinking of Schur's lemma is sometimes formulated. You take a complex irreducible representation. something that commutes with it, is a complex multiple identity. Right? That's what usually formulated as Schur's lemma. But this should be a real vector space. Our application is supposed to be a real vector space. Right? So is that still true for a real irreducible representation? Is everything that commutes with it a multiple identity? I claim no, that's not true for a real one anymore. I guess a stupid example would be a SO2 acting on R2. That's certainly irreducible representation. Anything SO2 commutes with it, that's not a multiple entity. Maybe more interesting application example would be SON acting on CN. So on Rn and then by complexification on CN. Right? That's an irreducible representation, but the complex structure commutes with it, and as an anamorphism from the vector space to itself, it's not a multiple entity. Right? So this commutes with, so regardless of two ends. And there I have a complex structure. It commutes with this action by definition. It is complexified, right? But it's not a multiple entity. So more general, for any complex representation, if you want to, there is some endomorphism that commutes with it, which is not a multiple entity. But one can understand how much this fails for irreducible representation compared with complex representation. It's not too bad. Like the exceptions are these kind of representations that commute with a complex structure, and then there are also representations that commute with, say, I, J, and K with a quaternion multiplication. And that's the only thing that can happen. But anyway, so here we use the symmetry of L in order to get our conclusion. Otherwise, in this train it wouldn't be true. Okay, so that's kind of an interesting application that the metric is unique, so you have to worry about what metric I'm choosing. To say it's a symmetric space is then true for any metric, and the metric is Einstein. So a very nice example of Einstein metric. Another, say, application or simple consequence that if M is G mod K, symmetric, simply connected, and G simple, this implies that M is irreducible as a symmetric space, and hence Einstein, for example. Right? So any symmetric space with G simple must be an Einstein metric. Proof is again very easy. If not, so remember, Hol P sits inside K, and Hol P naught sits inside K naught then. And since it's simply connected, it's the same thing as Hol P. So Hol P sits inside K naught. If the manifold is not irreducible as a symmetric space, then K naught, and hence Hol P acts reducibly on the tangent space at my base point, and then it splits. If it splits, then the isometry group, remember, also splits. But of course, this was assumed to be G, or G is I of M. Right? So this implies that G is equal to I of M is not simple. because the identity component splits us as non-trivially as a part of D groups. So G simple is implies irreducible. So for most symmetric space, you can see right away that the symmetric space is irreducible without having to say compute how K acts in the tangent space, and that representation is irreducible. So that's another useful observation. On the other hand, we should think of the following example, that I take G as a compact simple D group. With a bind-variant metric. So we know these are symmetric space, or what we discussed earlier. Right, so the symmetry, for example, at the identity was G goes to G inverse. And with the symmetry of the identity, since it's clearly homogeneous, it has a symmetry everywhere, so it's symmetric. But what's the isomorphic group? Certainly contains left and right translations, right? So sitting here side here is LG and RG. So I can say that G cos G sits inside the isomorphic group of the group G. It may not, so it's a non-trivial question whether it's the whole isomorphic group or not. But certainly I can say the following. So if I now want to write M, which is my group G, as a quotient of two of the transitive actions, well, G cos G sits inside here. So I can write it as a quotient of G cos G divided by the isotropic group at that entity. What's the isotropic group? Well, this here acts by a left translation, this by a right translation. So it's the elements G comma H applied to E as G H inverse. That must be E, so G is equal to H. So that's the diagonal. So this is G cos G divided by diagonal G. And how does diagonal G act on the tangent space? Via the adjoint. Right, because this was left translation and right translation. The isotropy identity is G is equal to H, so it becomes conjugation. Derivative of conjugation is the adjoint. So in this case, I get the adjoint. Okay. And of course, as G is simple, this implies now that G is an irreducible symmetric space. Because that group, that representation acts irreducibly on the Lie algebra by definition of a simple Lie group. Well, so maybe a word of caution. I don't quite know that this is a full isomorphic group, but I claim I don't care, because certainly it lies in there. Therefore, inside the isotroper, I have the diagonal G, and only diagonally G acts irreducibly, so the full one certainly would have to act irreducibly also. So it doesn't really matter having to decide whether it's a full isomorphic group or not. It's a consequence. Later on, we're actually going to see that this, after all, it is true. That if G is simple, then I0 of G is equal to G cos G. So what does it mean? It means that the set of all isometries fixing a point acts irreducibly in the tangent space. Right? That's the definition. So let's our point be the identity. So I look at the tangent space of G at the identity. The action is via left and right translations. So this here is LG, and this is RG. So I look at those which fix their entity. Right? So they're ones with G is equal to H. And I have to see how does it act on the tangent space by the derivative. Right? So I take the derivative of LG composed with RG inverse at the identity, and that's my action on the tangent space. That's my isotropy action. But this here, by definition, is the adjoint for the group. Right? By definition, what is a simple Lie group? It's one where the Lie algebra is simple, for example. Right? And one way when we talked about compact Lie groups, did we discuss that? The Lie group is simple if and only if the adjoint representation on the Lie algebra is simple. I guess so, right? If the adjoint preserves a subspace, it's an ideal. Right? Then the Lie bracket preserves it, so it's an ideal. A simple Lie group, there are no ideals, so it cannot be a product. Okay? Because this here is not quite strictly speaking correct, because this action is not effective. There might be some elements that act trivially. So inside here, what acts trivially at every point?
The center inside the L.
Correct. Divided by the diagonal embedding of the center of G. Right. This means fix the point G must be equal to H, acts by conjugation. That fixes every point if and only if G lies in the center. Okay. So this is the correct statement, that the isometry group is G cross G divided by the center, the identity component. But in general, there are other components. Okay. In fact, maybe I can write down what it is. So I of G, I claim, is I0 of G, multiplied, if you want to, by the automorphisms of the algebra G. So why is that? I could, for example, argue as follows. An automorphism at least preserves a killing form. Right? An automorphism is an isometry of the killing form. Well, is my binary metric a killing form or not? And would the automorphism preserve that or not? Well, I claim I can now use what we just proved over here. My compact simple Lie group is an irreducible symmetric space. That means the metric is unique up to a constant. That means every binary metric must be multiplied by the killing form. So you can say this implies every binary metric is of the family lambda times B. It's really only the killing form that counts as far as binary metrics are concerned. Automorphisms preserve the killing form, so they're also isometries. Inner ones sit inside here. They're given by adjoint, but outmod int adds extra components. So outer automorphisms which aren't inner, they in general give you more components than this harmony group. This was a long-standing open conjecture whether this is also true when the group is compact but not simple. So if it's a product of two simple groups, is this still true? The answer is no. There's some strange counterexamples. But for a simple Lie group, it's very nice. Okay. Let me just indicate the next topic a little bit I'm going to talk about on Wednesday. So here's a proposition. A is M locally symmetric. plus simply connected implies M symmetric. So remember, locally symmetric just means I have a symmetry on each normal ball around the point. It's not clear whether that extends to a global symmetry or not. And if it's simple connected, there's no problem. Then we can extend it to a global symmetry. That's part A. Part B. I have 3 parts maybe. Ah, yes. M is locally symmetric. If and only if nabla R is equal to 0. Which was, remember, if and only if R of x, y, z is parallel, if x, y, z is parallel. So a very nice characterization of locally symmetric spaces. This actually has a very simple proof, which I can explain in a few minutes, and it's a general principle again. So nabla R is a tensor of what type? It has type 4,1. Right, R is type 3,1. Plug in 3, I get 1 out. Nabla R is one more argument. It's type 4,1. And now I claim any tensor on G mod K invariant under G, which is assumed to be a full isomorphic group, with type K, L, such that K plus L is odd, vanishes. And so 4,1 sum is 5, so it vanishes. A very special case of a general principle. And what's the argument? I want to use it as a symmetry space, right? How do I use the symmetry space? I have a symmetry. So SP is an symmetry. And therefore it preserves the tensor. So what does that mean? Let's say you can interpret this as a tensor where I put in K plus L arguments and I get a real number out of it, equivalent way, right? SP preserves it. That means that if I put it into each argument, I get the same thing. Well, there are an odd number of arguments. It's minus identity. So it comes out as minus identity, and therefore it vanishes. Okay. So any tensor of odd order in that sense must vanish. Another example would be, say, the torsion tensor is automatically 0. Right? Of course, if I have a metric, I usually look at Levi-Civita connections, which means the torsion has to be 0. It's actually a consequence here, right? Because it has odd order. So it's a very nice general principle. Anything with order must vanish. So that's one direction. That's the easy direction. The hard one is to show the converse. If this is 0, why is it a locally symmetric space? So for this, I have to construct the isometry. And for that, I need some arguments with Jacobi fields, Jacobi equation, and the exponential map. I'll do that on Wednesday. So I don't know, you may remember such a formula, and I'll discuss it on Wednesday. How do I compute the derivative of the exponential map? Remember how to do that? So do you remember the formula? Pardon?
You can choose
Yes, J is along XPV. So take the dressing in this direction here, and J at 0 is 0, and nabla J at 0 is W. That's J1. For those of you who haven't seen it or forgotten, I can quickly explain it. This is very easy. And using that, we can prove the converse of this proposition also. To show this here, one needs a global version of that, which is called the Cartan-Ambrose-Hicks theorem. Cartan-Ambrose-Hicks. Anyone seen that before? So I'll explain that next time. It's actually a very nice theorem. It's kind of a global version of the computation one does with the exponential map here. Okay.
Is that something that Occam names as Cartan only?
That could be.
Not Cartan-Ambrose.
He doesn't prove it. I don't think. I think he just quotes it. So he proves this local version that, say, like in a small ball, when is the exponential map and an isometry. That's if and only if the curvature relates correctly. So there's a local version like that. Uses that to prove that a manifold constant curvature is one of the models, local isometric to a model. Right? But there's also a global version of, I can write one as a cover of another if the curvature relates in the proper way. And that Tokama doesn't do. But I think he refers to something like that, and I forget what he calls it. There's a theorem in Chiga-Eben. Chiga-Eben does it very carefully. And he calls it the Cartan-Ambrose-Hicks theorem. I'll discuss it a little bit on Wednesday.